We're going to jump back to the beginning. If you recall, I first started off with these slides. If you paid attention, I quit halfway through, and now we're going to finish them out because we took a rather long detour, and now we're going to jump back, and hopefully it'll make at least a little more sense. Quick recap. Remember, one point of the slides was to think about what are the different ways to think of a processor. And at first we thought of it as a quantum level where you basically just have electrons flowing around in certain ways. If you were able to magically make your electrons flow the right way, you would have a processor. Next, you can make conductors, insulators, and semiconductors, glue them together, and you can have a processor. You just have to put them together correctly. Of course, you can dope silicon to turn into diodes and transistors, and when you have a bunch of diodes and transistors, if you hook them up right, you have a processor. You can then think of it as gates, as AND gates, Boolean logic, and of course our truth tables, which we just spent a ton of time on. You can think of a processor as just a bunch of these gates glued together. Those are different ways to think of a processor. Next, we're going to zoom through to the combinational logic, which is where we kind of start to depart because you use muxes and decoders and other things, but you're going to have to use other gates as well. All right, everyone get this? Zooming through. All right, whoops, too far. All right, how does the computer do math? We're going to start with math because adding is a very pivotal instruction for computers to do. It needs to be able to increment and be able to jump memory spaces, which requires adding. So how do we do adding? Well, hopefully, wait a minute. Do any of y'all have to do the new math? What's that one called now? Common Core, yeah.
I think she showed us a little bit in discrete on Tuesday because she was saying how her daughter had to do like math and she was explaining it to us. But other than that,
my brother has to do it and it's really confusing.
No, well, I know what they're doing. I think it's counterproductive, but I understand what they're trying to do. Well, but did any of y'all have to do it? Good. All right. Well, that just means I don't have to explain it a different way. So you remember in grade school, 125 was really just 5 times 10 to the 0th. 10 to the 0 is 1. So 5 times 1 is 1. The 2 is 2 times 10 to the 1st, because 2 times 10 is 20. And that 1, the leading one's a hundredths digit, and where it's 1 times 10 to the 2nd, aka 100. 1 times 100 is 100. Binary. And by the way, that's how you get your 125. It's really 100 plus 20 plus 5. That's the point here. The reason I broke it out that way is that's how numbers are stored in computers, so just in binary. So it's 1 times 2 to the 4th, which is 16. 0 times 2 to the 3rd. 2 to the 3rd is 8. It's 0, so we don't add that. 1 times 2 to the 2nd, that's 4. So we do add 4, so we get 16 plus 4, we have 20 so far. 1 times 2 to the 1st, 2 to the 1st is 2, so we add 2, that's 22, and then 2 to the 0th is always 1, and we add 0, so this number is 10110 represents 22. Did y'all go through that in procedural or not too much? Oh wait, you weren't here. Did you do this in procedural?
I think we did more in networking a little bit.
More in networking?
More networking.
Okay, cool. So, the addition happens very similarly. You know, decimal additions, you add the 2 because you're taught regular math. I mean, normal math. Carry the 1, it's a 6. Don't carry anything, and then there's 3. Morning. I guess he just didn't want to do architecture. All right. Whew. So binary addition, same thing, except for your digits are 0 and 1. So 1 plus 1 is 10. Nice. Or 1, 0. So you have to carry the 1. 1 plus 1 again is 1, 0, or 10. Carry the 1. 1 plus 0 is 1. And 1 plus 0 is 1. Boom. What's that number?
1100.
In decimal?
12.
Yes, 12. 8 plus 4. So we want to build an adder. and we're going to call it a half adder. It'll make sense why it's called a half adder once we get to the full adder. But you have A and B, which are your two inputs, and S is the sum and C is the carry bit. Okay, you need to carry something afterwards. So there's the truth table, and this truth table hopefully makes some sense because 0 plus 0, the sum of that is 0, and there's no carry bit. 0 plus 1 is 1, and there's no carry bit. 1 plus 0 is 1, no carry bit. 1 plus 1 is actually 1, 0, so the sum is 0, but you need to carry out an additional bit. All right, what's the circuit to this? By the way, anyone else need this K-map before I erase it? Good. Let me make this a little clearer. All right, trying to figure out a circuit for this. Might help if you just look at one output at a time. So the carry, what's the carry? That one's going to be easier. It's only on when both A and B are on. That makes it a, all right. All right, well that was easy. Yeah, how about sum? Well, it's almost like an OR, except for that last one.
XOR.
It's an XOR. Wow, that was a really pointy bullet. All right, how are we doing? What's the gate delay? Someone said 3. Why is it 3?
Because those would be happening in tandem. The maximum time the AND gate would take would still be less than the XOR's time, so you
Right.
just take the XOR's time of 3.
So they happen,
Either way.
yeah. Tandem, in parallel, same thing, just trying to keep the words the same. They happen in parallel, so they're capitalizing on parallelism, and therefore it takes 3 gate delays to do this half adder. All right. Half adder, let's see, whoops. So combinational circuits, we talked a little, mentioned this, but didn't ever really define it. Output is determined exclusively by the input. So there's no internal state. We already talked about memory registers. And the reason I start that earlier is so you can get used to Verilog, because a lot of students have problems with Verilog. But output's determined exclusively by input. There's no memory. So a half adder, that's an example, because there's no internal memory to a half adder. A decoder selects a given line via an index. So the example here is that if you select 0, 0, it selects outline 1. If you select 1, 0, in this case that's the value 1. You have to think of this as reversed because A sub 0 comes first and then 1. Then that's line, the second line. 0, 1, which is really 1, 0, is the 2, which is the third line, and then 1, 1, which sums up with 3, makes it the fourth line. It's just like in C, the 0 counts. A mux is the other way around, kind of, sort of. So you have inputs A and B. If your selection wire is 0, I'm sorry, for your mux you have 3 inputs, A, B, and S. And S selects what the output's going to be. So if it's 0, it forwards A, and if it's 1, it forwards B. So a decoder activates a single line based on the input, and a mux forwards a selected line based on multiple inputs. And these decoder and muxes are going to be very helpful for building your processor, so make sure you understand how they work, which we will get to right now. So let's build a, what is this, a 2-bit decoder. So out 3 is just an AND gate. Perfect. Out 2 would be an AND gate if A naught is inverted, right? Do y'all see that? Look at the truth table. If you notice about the decoder, you're only activating one line, and an AND gate always activates one line, so you just need to set up the input so that it always activates correctly. If you, for A naught, you invert A1, and for the final one, you invert both. Hey, look at that. So what's the gate delay here? We got 2? 2? Yeah, 2. I will take 2 or 3 depending on what you prefer. The knots do take 1, but a lot of times we ignore the knots. And I don't think I actually mentioned why a lot of times we ignore the knots. Why do we ignore the knots? Think of your memories. Your flip-flop has how many outputs? Two outputs. What are the two outputs?
Q and not Q.
Q and not Q. So your memories are actually producing, Q and not Q, which if you're using a memory machine, that means your A naught actually has 2 lines, we're just not showing them, and one of them is the not line. So when you use a register, you're already getting the not line from the values, so you can just wire that up as opposed to pay the cost of the not. That's why a lot of times we ignore the not, and why for your assignments I will let you either ignore the not or keep the not, or have the not take 1 gate delay. You good, Perry?
Yep.
You sure?
Positive.
Okay. All right. So, any questions on the decoder? Nope. All right. How about the mux? Input S selects either A or B. Oh, well, I guess I just give you the circuit. All right. So, if you think about it, what they first do is they put an AND right after each input, and the selector is the option to it. So if it's selecting one, it just makes sure S is that value, and on the other side, it makes sure that it's not that value. The issue is you have 2 lines coming out, and you somehow have to combine them. One is active, the other is going to always be 0. And so if the other one's always going to be 0, if you OR it, then you can combine it into one line and have a correct output. Okay. Does anyone need that explanation again? That can be a little confusing.
I do.
You do?
I do.
All right. When in doubt, write out the truth table. When in doubt.
That's just my go-to.
It's gonna be when you really cannot figure it out, just write the truth table. It is long and painful, which is what you're just asked me to do, but that's why I'm paid. So let's do it. What's the full truth table? We have 3 inputs, A, B, and S. And one output, C. We'll do 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Are those all the options? That should be 8 options.
Should be.
And let's draw the circuit diagram. Grab the bullet. really hard to draw this OR. I never get that OR down. You gotta curve it at first and then really curve it again. All right, 0, 0, 0. So S is gonna be 1. I'm gonna write down the S's so it makes this easy, and then hopefully y'all can at least remember what 2 values are. So S is 0, right here. Bless you again. A is 0, so 1 and 0 is
0.
and 0 and 0 is
1. Oh, 0.
0. This is not an and, it's an and. 0 or 0 is 0. S is selecting A is 0, and which equals C. We're good. Let's do it again. This time we're flipping the S. A is 0, 0 and 0 is 0. 1 and 0 is 0. 0 or 0 is
0.
so the 1 is selecting B. B is 0, C is 0. We have the right output. I just realized that I should have written S first. A is 0. 0 and 1 is 0. S is 0. B is 1, but 0 and 1 is
0.
0, and then we have 2 zeros going to the OR, so C is
0.
so we're selecting A, and A is 0, so C is 0. How are we doing so far? Almost there? All right, let's keep going. Let's keep going. Let's see. Back to this version. S is 1, so we knot it to become 0. A is 0, so 0 and 0 is 0. S is 1 and B is 1. All right. 1. So we have 0 or 1, so C is 1. S is selecting the second one, which is B, and its value is 1, and C, and it outputted 1, so that's correct. In other words, this column needs to match whatever's being selected over here for this mux to be correct. Okay. S is now 0, so we got a 1 up here and a 0 down here. A is 1, so 1 and 1 is 1. And then 0 and 0 is 0. So 1 or 0 is 1, sorry. So it's 0, selecting A, there's the 1. All right, how are we doing now?
I mean, like, I get the truth table aspect of it, but how do you know which one you're selecting? That's what I don't.
How do I know which one I'm selecting?
I get the outputs as far as like a truth table is concerned with the whole A, B thing. I don't believe.
So A and B are just some inputs, and S is selecting it. So the idea with a mux is you have 2 inputs, but you only want to select one of them. So that's what S is. So you have 3 inputs in total. S selecting A or B. And so depending on which one you select, and I'm going to pretend this one, otherwise I'd be giving you the finger, it would select whatever value that is, whether it's 0 or 1, and forward it along. So it's the S is forwarding along a certain value. Which value? The one it's selecting. So if it's selecting B and B is 0, it forwards 0. If it's selecting A and A is 1, it forwards 1.
So it more depends on what S is than A or B?
S, yeah, it first depends on what S is, and then depends on what S is selecting is. So you can think of it as 2 levels. First, what it selects, and then what that is it's selecting is.
Okay.
Hopefully I don't have to do any more of the truth table. This is called a 2x1 mux, since it has 2 inputs and 1 output. And before we answer that next question, what's the gate delay? 5. 5 if you include the knots, or 4 if you don't. 5 or 4. All right, so this is a 2x1. How would you build a 4x1 mux? You have a 2x1 mux. How do you build a 4x1 mux? Not necessarily together.
You need.
Oh, by the way, we have a special symbol for a mux. It's a trapezoid on its side. Oh, we want to have 4 of them. S must have 2 bits, because if you're going to select from 4, you have to specify with at least 2 bits, because it requires 2 bits to go from 0 to 3. Uh-oh, so we can select between these two, and then what do we do? Does it give a picture? It doesn't. Lame.
So you connect them to demand.
Connect with another mux.
Yeah, here we go. But what's the input of this mux going to be?
The output of the previous loop.
It's a, there's another S, S2.
Well, I'm trying to remember if I actually did this part correct, because I may not have. So that S0 will select the A or the B, sure, and that one will select that. So then this one is selecting whether you're selecting the first one or not. So I think that's S0, because, or it's S1 actually. Yeah. Because S1 will select C and D, which one there, and up here will be S0, that's the first bit, which is, oh no, that's not selecting that at all. So which one's which, guys? Let's write the truth table. Oh man,
I don't think you have a number.
I'm not gonna write the whole thing out. And it's one output. Wow, that's amusing. This is, well, we'll make this easier. A, B, C, D, 0, 0. What's the output? We need to be selecting A. A, B, C, D, 0, 1. The output needs to be B. Because this selects the first one, A. This selects the second one, B. That needs to be C. All right. So, in the top one, we need to select A. So it would look like you'd want this. Let's see if that works. And then we don't care about that one yet. All right, here we want to select B. Uh-oh. Which means we really want S1 right here. And that would still work for A. Great. Because SZ would be selecting the first one. Okay. Down here, we need, I had it backwards, S1. Put in the truth table, things help. Because S1 is 0, that'll select C from here. I mean, S1 is 0, that selects C. S0 is 1, which will select the bottom one, and then output C. So it's 3 muxes. And what's the gate delay? Yeah, 8. Let's say 8. These two happen in parallel, but this one requires both of them. So it's 2 muxes are in sequence or series.
Would 10 also be an acceptable answer? because
Yes,
of the knot?
yeah, because of the knots, correct. All right, the adder is a basic gate of LU, decoder is a basic gate of indexing. AK, you want to select a wire. This will make a lot more sense when we design our first, let's see, circuit, finite state machine, because the first circuit we create will not be an actual processor, it'll be a finite state machine. Decoder, and see, MUX is a gate of controlling data movement. AK, we want to forward this data, not this data down here. These are very common circuits to be using. That's why they are given special images, especially the MUX, and the decoder is usually a large rectangle. All right. Now, this goes through just to recap, just to make sure we're all on the same page in case you missed it. Gate outputs do not change exactly when the inputs do. They are as a delay. It's about the speed of light, and saturation time, or what I call gate delay, is to how long it takes a transistor to make the switch. Every combinatorial circuit has a propagation delay. Time between input and output stabilization. It is important to think of it as stabilization because the output will fluctuate up and down until it finally stabilizes to the correct output. And here we go with some delays. Hey, look, we have our MUX, gate 1 and gate 2, so we have our inputs. Notice that X rises up, or S, sorry. S rises up, and the delay from gate 2 is how long it takes Y to rise up, and then gate 3, or delay 3 is how long it takes for C to rise up to the correct input of Y. That's why there's a serial delay. And you can look over here and have a very similar reaction as well. Here we go. What is the gate delay of this circuit?
Do we know what gates are?
Hmm?
Do we know what the gates are?
No. You have circles. Think of it mathematically, not, or algebraically, maybe I should say, not actual concrete numbers. So what gate delay do you have to pay for?
It's got to be at least 3.
All right, let's think of it this way. G5, you always pay for it in full, right? I mean, you pay for all of them in full, but no matter what, everything has to go through G5. Nothing is happening in parallel to G5. So when you answer this, you start off with what you have to pay in serial or in series, and that is G5. So it's going to be G5 plus something. Well, what do you add to G5?
G3.
Maybe. I mean, yes, that would give you a lower bound.
I'll say either G3
But
or G4.
notice you have 2 branches coming in. So, and you want to take the max. And the top branch is G1 plus G3, and the other one is G2 plus G4. So you have to compute what those two are, find the maximum, and then add that to G5. Because the maximum of those two is how long it takes for the correct inputs to arrive at G5. We good? All right, this is a good time to stop. That way everyone can have a 10-minute reprieve until our guest speaker arrives. And also, we get to stop before we start talking about clocks. I'm actually going to stop this presentation and go back to finite state machine, because at that point afterwards, it'll make sense why we actually have a clock. The next presentation is actually very important, even though there is no assignment to it. It's very important because it's going to transition from what we've talked about so far to why we have modern processors. So please come in. It'll help you in understanding a lot about how computers work. All right, let me go to at least Scrum Do, because I just realized I forgot about that.